The next section is on Wilson's theorem. So it's in 1770 that the English mathematician Edward Waring announced many new results in one book, and one of those results was by his former student John Wilson, which states that if P is a prime, then P divides P minus 1 factorial plus 1. P divides this number. John Wilson most likely came up with this from numerical evidence, but neither Wilson nor Waring was able to prove this result. So it was announced in 1770. 1 year later, in 1771, Lagrange came up with a proof. But Leibniz seems to not have got his fair share of credit, because there is evidence that Leibniz was aware of this result almost a century before it was announced. But anyway, the name of Wilson remained with it, so it's known as Wilson's theorem. So that's what the theorem is. It says that if P is a prime, then P minus 1 factorial plus 1 is divisible by P, which means if we express it as a congruence, P minus 1 factorial should be congruent to minus 1 modulo P. So let us now see the proof. The proof you will see is not very complicated, which may make you think why Wilson or Waring were not able to come up with the proof. See, the thing is that the right idea doesn't always come so easily. Once it comes and once you have a proof, it seems like it was very easy. But it takes time, and no one knows to whom the right idea will come. It may be anyone. Okay, so let's see the proof. The first two instances of P can be checked very easily. The first instance, of course, is the even prime P equal to 2. What happens if P is 2? What is the left hand side of this congruence? 2 minus 1 is 1. 1 factorial is 1. Is 1 congruent to minus 1 modulo 2? Yes, because 1 minus minus 1 is just 2, which is divisible by 2. So that means when P is 2, this congruence is correct. It's true. What about 3? If P is 3, then 3 minus 1 is 2, 2 factorial is 2, and 2 is congruent to minus 1 modulo 3. Again, because 2 minus minus 1 is just 3. So we can start the proof by making this observation. The case is P equal to 2 and P equal to 3 are easy. Okay, so let P be greater than 3. That means P is at least 5. Now let A be an integer in this set, the set of all positive integers less than or equal to P minus 1. Then A is co-prime to P, relatively prime to P. Why? Well, that's because A is positive. Coming from this set, A is positive and A is less than P. That means P does not divide A. And this condition and the fact that P is a prime tell us that A should be relatively prime to P. Then GCD of A and P is 1. So by the theory of congruences, this congruence AX congruent to 1 or P has a unique solution modulo P, and the specific theorem is theorem 47. It's coming from there. You remember the theory of congruences, which tells us that you have to calculate whenever you have a linear congruence, theory of linear congruences, whenever you have a linear congruence like this, you first calculate the GCD of the coefficient and the modulus, in this case A and B. If that GCD divides this other number, then only there exists a solution. And if that GCD is say D, then there are D incongruent solutions. In this case, that GCD is 1. So there is a solution, and only one incongruent solution means modulo P, there is only one solution, a unique solution. So there exists a unique integer A prime in this range that will satisfy this congruence. Such that A prime is congruent to 1 modulo P. Now this, you see, A is coming from that set, from set of integers, all positive integers less than or equal to P minus 1. So is A prime. A prime is also another such integer. A may be equal to A prime, but that will happen precisely in this situation, since P is prime, A is equal to A prime if and only if either A is 1 or A is P minus 1. Exactly why that I am leaving to you to figure out. It's actually given there, something is written there in the book. So you go through that and see why this is true exactly. Okay, so precisely when A is either 1 or P minus 1, will this A prime also be equal to A? That is, these are the only two cases where A and A prime will be equal. In all other cases, for all other values of A which are neither 1 nor P minus 1, the A prime will be different from A. So we can group because of this fact, we can group these integers. From all the positive integers less than or equal to P minus 1, if we remove 1 and P minus 1, we are left with these integers. So we can now group these integers into pairs such that A is different from A prime and A prime is congruent to 1 modulo P. So how many such congruences are we getting for this type of A's? In total, we will get half the number of congruences, the number of congruences of this type will be half the number of integers here, because we are considering pairs of these integers and creating one congruence for each such pair. How many elements do we have in this list? P minus 3, because we have removed 1 and P minus 1 from those P minus 1 integers. So, P minus 3 divided by 2 pairs are present here of this type. So, that many congruences are there. Now, if you multiply these congruences, multiplying this many congruences and rearranging the factors, we will get what? We are actually going to get these numbers again. We don't really know with which a prime will come in the congruence, but at least we know that if you take into account all the congruences and multiply them out, then the left hand side would consist of precisely these integers. So, you would get this. That is why we say after rearranging P minus 2, but the right hand side will be a product of this many ones. So, this is just 1 modulo P, or 1, you can of course consider a 1 here, that is always there. So, P minus 2 factorial is congruent to 1 modulo P. Now, what you can do, you can multiply both sides of this congruence by P minus 1. So, that way the left hand side will become P minus 1 factorial and the right hand side will be P minus 1. However, P minus 1 itself is congruent to minus 1 mod P. So, that is how we get our result. Just one more line. That is the proof of Wilson's theorem. Now, you can see this proof more concretely in this next example. This is example 4, I think, yes. Now, in this example, you consider the prime 13. Okay. So, the relevant congruences, 13 minus 3 is 10, 10 divided by 2 is 5. So, these congruences that we multiplied here to get this one, in this case we will get 5 congruences like that, and those 5 congruences are this. You can see for yourself. I mean, if you consider all the integers, all the positive integers less than or equal to 13, you get these integers, no? So, this is your 1, this is your P minus 1, which you are ignoring and considering the remaining integers. From them you have to create those pairs, and the congruences we get are these. 2 times 7 is congruent to 1 modulo 13, then 3 times 9 is congruent to 1 modulo 13. What else do we have? 4 times 10 is congruent to 1 mod 13. Then 5 times 8 is congruent to 1 mod 13. And finally 6 times 11 is congruent to 1 mod 13. Just give me a moment, okay? Okay, so let us also see briefly if these really are correct. 2 times 7 is 14. 14 minus 1 is actually equal to 13. So obviously divisible by 13. This is 27, right? 27 minus 1 is 26. 13 times 2 is 26. This is 40 minus 1, that means 39. 3 times 13 is 39. Again 40, and this is 66 minus 1, 65. That is also divisible by 13 because 5 times 13 is 65. So you can see that these are the concrete congruences that you abstractly saw here. Now if you multiply these congruences, you can see that these numbers between 1 and 13, excluding 1 and 13, have come in whatever manner. So if you now multiply these congruences and rearrange the terms, what will you get? You will get this product. And are you actually getting all the terms here? I mean all the integers. Let us see 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes. Oh, what about 12 though? Am I missing something? P minus 1. Oh, sorry. Yeah, I made a mistake. I had to write till 12 only. No, not 13 itself. So this will be 12 and this will be 11. Yeah, that was the mistake. Sorry about that. Yeah, now it makes sense. Not this, but this. So this will be congruent to 1 modulo 30. That means we are getting 11 factorial is congruent to 1 mod 30. So if you now multiply by 12 on both sides, you get 12 factorial on the left hand side and the right hand side becomes 12, which itself is congruent to minus 1 mod 30. Yes, so that's how you are getting this Wilson's theorem for the prime p equal to 13. Now, as Lagrange observed, the converse to Wilson's theorem is also true, and the proof is very small in fact. Let n greater than 1 be an integer for which n minus 1 factorial is congruent to minus 1 mod n. The claim now is that n is a prime. Suppose it's not a prime. Okay, because it's greater than 1, being not a prime means n is composite. And so you will get some integer d which is greater than 1 and less than n, and also it divides n. Okay, so some such proper divisor of n will exist which makes n composite. So this is our supposition. But now something will go wrong. You see, because d is less than n, that means d is less than or equal to n minus 1, right? And that is why when you write n minus 1 factorial as what it is, that is 1 times 2 times all these integers up to n minus 1, one of those factors will be d, and that's why d divides n minus 1 factorial because of that. But at the same time, what are we getting from this congruence? This congruence also tells us that n divides n minus 1 factorial plus 1. But D is already dividing n and divisibility is a transitive relation. So D also divides this. Now you combine this divisibility relation and this one and conclude that D divides this minus this. That is, i.e. D divides 1. But this is a contradiction, because D is greater than 1, it cannot divide 1. That is why our supposition that n is composite is wrong. So n must be prime. So combining Wilson's theorem and this converse, we can say this: for any positive integer n greater than 1, n is a prime if and only if n minus 1 factorial is congruent to minus 1 modulo n. Now it seems like we have got a test for primality of an integer that's greater than 1. You have some n and you want to check if it's prime or not. What you do, you calculate n minus 1 factorial and see if it's congruent to minus 1 mod n. If it is, then by this converse n will be prime. But if it is not, then by Wilson's theorem n will be composite. But this is an impractical test. Why? Because for small values of n, we already have other means of checking whether n is prime or not. But for large values of n, n minus 1 factorial becomes so large so rapidly that it becomes unmanageable. You cannot calculate this very easily, even though it is simply a product. It will become so large that you cannot work with it. So then how can you, verifying this congruence itself will become a Herculean task. So that is why it mostly has theoretical importance, not computational importance. Okay, so there is one more result after this, which actually we have seen in Herstein's abstract algebra, but we will do it in the next number theory video. And tomorrow we have class 11 mathematics. So what I have decided is, let us start class 12 tomorrow, and then we will alternately do 11 and 12 mathematics. So that will be all for tonight. So see you tomorrow with the class 12 maths. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.